Hi, y'all. Today we're going to try to understand the basics of how a motor actually works. And what a motor does is it takes electromagnetic energy and transforms it into motion. And hopefully y'all watched the YouTube video that I provided a link to on D2L that should be watched before you watch this video. So that was something that somebody else put together that honestly we would have done a similar exercise in lab if we'd been in session. So you guys would have kind of made a very similar motor to what you saw in that YouTube video. All right, so what I've got in this picture here is basically a loop of wire, and we notice that the wire's got current running through it. Okay, so let me point out the current here. So there's current running up and then current running back down. So that means that my current right here is going upwards, and my current there is going downwards. Okay. All right, and now we're just going to think about what happens to this coil of wire as a result of the fact that it's exposed to a magnetic field. The direction of the magnetic field lines are drawn in the picture. And we're going to think about kind of the right-hand rule for side one, which we can see the sides are labeled. There's side one and side two. So for side one, the current is going upwards, up to the top of the screen. Okay, so up to the top of the screen, maybe like this, up to the top of the screen. And the magnetic field is going to the right. So basically, you should be holding your palm up so that your fingers point to the sky and the palm of your hand is to the right. And when you do that, you see that your thumb is pointing into the screen. Okay, so there's a force on side one that points into the screen. Let's look at side two. So for side two, and this is going to be really awkward, but my fingers have to point down and the palm of my hand points to the right. And if I'm sitting here doing this, if I'm a student, then my thumb should basically be pointing away from the screen now. The fingers go in the direction of current in such a way that they can curl in the direction of magnetic field. There we go, fingers point in the direction of current, palm points in the direction of magnetic field, and your thumb shows the direction of the force, so the force is towards you. And then we can picture what these two forces are going to do to this particular coil of wire. It's going to tend to make it kind of rotate clockwise. Clockwise, if we think about looking down from the top of this shaft right there. So let's look at another view of this. Let's look at the top-down view, which has been provided to us on the next slide. There we go. So this is a top-down view, exactly what we're talking about. Previously, we see that this force there basically is this force that's on side one that would point into the screen over here on the left-hand schematic. And then side two, the force points that way, which would be out of the screen again on the left-hand schematic. So this is on the right-hand side, this is a top-down view, and this entire thing tends to rotate around clockwise, okay, at least for the moment that's shown. Okay. So we can do a little thinking here and think about, well, when is the torque, the rotation that this magnetic field causes going to be maximized? We can look at the top picture here. Will show when we've got maximum torque. So let me grab my pen. That side right there, the left side, we've got current coming out of the screen. So current coming out of the screen, so fingers pointing towards you, and then magnetic field points to the right, thumb is upwards. So we would definitely have a force that points upwards on the left-hand side of this loop of wire. On the right-hand side over here, our current is going into the page. So current's going into the page, And then the magnetic field points to the right, and my thumb is pointing down. So there we go. So we can see that when we've got forces arranged like this, that we really are going to tend to spin this coil of wire really well. All right, so awesome. What happens when it gets to a position where the coil of wire is basically perpendicular to the magnetic field? Well, now let's see. Our current is still on that one side. Let's see, right there. Our current is going out of the page. So current going out of the page, magnetic field to the right. My thumb is pointing upwards. Okay. And then on the bottom there, the current goes into the page. Okay, thumb is pointing downwards. Okay, so what's going to happen here is, well, we're definitely not going to tend to get any kind of extra stimulus to rotation. Instead, what's going to tend to happen is this thing's going to tend to flatten out. Now, what's interesting is if we maybe do one more drawing here, which is not provided, but I will do my best. Let's do one more drawing. So there's my my kind of loop of wire over here, and over here are my two sides. Okay, and right here I've got what? I've got current going out of the page. Here I've got current coming into the page. So it's just like if I've taken this one right here and rotated it just a little bit further. All right. And now let's draw in the direction of our magnetic field as well. So our magnetic field is pointing to the right. Okay, and now let's think about the direction of the forces. When I've got current coming out of the page and magnetic field going to the right, current, this is really awkward. Current coming out of the page, magnetic field going to the right, my thumb points up. So as a result, the force on this guy is going to be upwards. Well, okay, the force on this guy down here is going to be downwards then. So what's that? What are those forces tending to do? They're actually tending to slow down the rotation and cause it to rotate in the other direction. Okay, all right. This is important in motors because what do we want for a motor? We want something that constantly spins in the same direction. But what we have here, unless we make some modifications to it, is something that's going to tend to flip-flop just back and forth. And in my searching of YouTube videos to try to find one that showed a motor that was correct, I showed a bunch of people claiming that they had made motors. But what they'd really made was a flip-flop paddle. And if you watch the videos closely, you could see that the direction of motion actually changed from being maybe this way to being that way periodically. All right, so a motor, with a motor, we have to somehow maybe interrupt the current through half of the loop's journey. At least that's the way it works for a very simplistic motor. There's probably, there is a better way to do things, but for the sake of our discussion, we'll just go with this kind of simplistic view of how to build a motor. All right, so we got a lot of math on this page. It's great, it's fine. One thing I want to point out is I just want to remind you guys of the torque equation. So this was one from last semester. And it said what? That torque is equal to RF sine theta. That's, what is that? Torque is equal to RF sine theta. So that'd be, you know, from our center of rotation there is R, and then the force F there, and then I guess they've got a phi on this one, but that angle right there is the theta. All right, so we can do some analysis here. We can add up the fact that I've got a torque on this side, I got a torque on that side, which is what we're doing up at the top. But the end result is just going to be this thing right here, that my torque is equal to capital N, which what in the world is that, times I, that's current, times capital A, that's the area of my loop. So literally in this one, it'd be like length times width there because, well, it's a rectangle. times B, that's magnetic field, times the sine of phi. We'll talk about phi here in a moment as well, but first let's knock out this N. N is the number of turns of wire. It's kind of a weird way to put it, but it's basically like the number of times your wire is wrapped around. So you could have just a single loop. If you had a single loop, that'd be an N value of 1. If we maybe made multiple coils here, maybe turned the wire around 4 times, well, we basically have 4 turns of wire. And that's what capital N is. This, this phi, on the other hand, so let's talk about phi. Phi is the angle between the magnetic field and the normal to the area of the loop. So remember, normal is just a math word that means perpendicular. So what we're looking at is the perpendicular line there coming out of the loop. So let me clear that. We'll erase. So we're looking at that perpendicular line coming out of the loop, and phi is the angle between that perpendicular line. Wow, my hand's really shaky. Phi is the angle between that perpendicular line and the magnetic field. So right there is my angle phi. Let's see what happens then. If I continue to rotate this coil, or maybe I put it back this way, so maybe there's my coil, my angle or my normal would be sticking out right there. The angle between my normal and the magnetic field, in this case, would be what? Well, first off, what I've drawn there is not phi. Okay, so let's erase that right there. Okay, so that's not phi, what I just drew. What is phi? Well, there's my normal. My magnetic field is right there. My normal's there. My magnetic field is there. What's the angle? The angle is 0. Phi there is 0 degrees. What's sine of 0 degrees? 0. Okay. So when I've got the loop in this particular orientation that I've drawn, my torque is going to be 0. Okay. All right. Great. So when is my torque maximized? All right. So if I have my loop maybe in this direction, the normal is going to be straight out. And now I've got an angle between this normal and look at the magnetic field. The magnetic field right there. What is that? My phi now is 90 degrees, and sine of 90 degrees is 1, and that's when my my torque is maximized. All right, so here's a problem. We've got, let's see, a coil of wire with some area, consists of 100 turns. It has a current of 0.045 amps running through it. We've got a magnetic field of 0.15 Tesla. And so what do we want to figure out? We want to figure out what the maximum torque. Well, this is not bad at all because we've just got this equation, NIAB sine of phi. When's my torque going to be maximized? Well, my torque is maximized when phi is 90 degrees. So this actually is just a straightforward kind of plug and chug problem. And let's see. And there it has been plugged and chugged. And we see that our maximum torque is 1.4 times 10 to the negative 4 Newton dot meters. All right. So earlier I mentioned that we don't want the current on all the time, because if we do, the way the direction of our forces switch is going to cause a switching direction of torque. And instead of having a motor, we're going to have a flip-flop paddle. So how do we get around that? Well, we get around that in this simple design right here by basically having breaks in the contact between the metal ends of this loop of wire and the power source, the battery that's actually driving current through it. So the places that I've got circled over here on the right, maybe we would have some plastic pieces in there or something like that. It's more complicated than this, but at least it gives us the idea of kind of what a basic motor looks like. So again, we're taking electromagnetic energy, we're taking stored um, electromagnetic energy and transforming it into what? Into motion. Um, so this is how your car works. Now you know everything. All right. Maybe not. Talk to you in a little bit.